learning about a forest is kind of like learning how to read. And I'm re-experiencing this with my kids, as they learn how to read, first they didn't want to read because it was difficult. They had to learn new words and things like that. And the more they've read, the more they like to read. Now I can't keep them out of books. And it's kind of an analogy in my experience with forestry and forests is the more you learn, the more you want to learn about it, because all of a sudden, they say you can't see the forest for the trees. It's this green mass of big things out there. But then you learn the species. And then you learn the individual physiology of each of the species. And you learn all the organisms that connected with this species. And so, for me, when I go for a walk in the woods, I rarely get lost, and I'm never bored, because there's always a million things to look at. And I don't get lost because every situation, every tree is unique, and I remember those uniqueness things as I go by them. And when I go hiking with my family and we go back, and I said, well, didn't you remember this tree that had the weird crook on the top? And I never even saw it, and so things like that. So, granted, this is my area of passion, so I find it interesting, and not everybody finds the same things interesting. But if some of this stuff seems a little arduous to get through, I mentioned that, bear in mind that the more you deal with this, the more you look at it, the more interesting it gets, because the more you see out there. So I kind of put this together, work with a lot of landowner groups out there. Everybody has the same objective, really, and that is to keep their forest healthy, at least the ones that come to the workshops. I mean, the ones that don't come to the workshops are already indicating they're not interested, so I don't usually end up talking to those folks. So this is a program that's really geared at Montana. For me, Montana forests are very, very interesting. We've got 9 major species that we're working with, each of which has slightly different nuances. We have incredibly diverse forest ecosystems. You can walk 300 yards and walk through 3 different, unique natural histories, forest vegetation types, things like that. I'm sure you can do that here in the Black Hills. I'm not as familiar with it. But that's partly due to how our climatic patterns work across Montana. So this presentation is a little bit focused at Montana forest ecosystems, but there's a lot of similarities with the Black Hills. The biggest difference is you're predominantly dealing with one species, and that's ponderosa pine. Even though you have birch, you've got aspen, you've got spruce, and I understand a small pocket of lodgepole pine in one location. You got bur oak. So, you're dealing with a different assemblage of species, with the dominant one being ponderosa pine. So, when talking about forest health and sustainable forestry, that in my neck of the woods often involves some discussion about harvesting, because harvesting is a tool that earns you money, allows you to do other stuff. And one of the questions that always comes up that even our advocacy groups may not have a good handle on is, what the heck is sustainable forestry from the sense of harvesting trees? So here's a question. On this landscape, this is where my property is, where I live. The yellow trees are larch in the fall out there. And so the question is, assume you have 1,000 acres and you're growing trees to a target age of 100 years, which by me is going to be a ponderosa pine about that big. Okay? How many of those trees can you harvest in something called a sustainable fashion? Okay? And this is a little bit of a simplistic view, but if you got 1,000 acres and you're growing them to 100 years of age, and you want to harvest a certain number of trees every year, and you're just going to go by acres, the answer to that question, and you may already know I guess I didn't have that on there, is 10 acres per year. This is how we do sustained yield harvesting. Because if I have 1,000 acres and I can consistently grow trees to 100 years of age, if I harvest 10 acres this year, by the time I harvest my last 10 acres, my first 10 acres that I harvested, the regeneration on there will be 100 years old again. And that way I'm never cutting more trees than are growing on that landscape. And so this is what we really mean by sustainable forestry. Now, it gets more complicated, of course, because you have mortality to insects and fire and disease. Trees don't always grow at the same rate. Some may grow faster, some may grow slower. You have drought. All of those types of things you have to play into it. But the fundamental thing is, in any kind of forest, to manage for sustainability, you don't ever want to harvest necessarily more than you're growing, unless you're willing to defer. Now, I could harvest 20 acres every other year. It'd be the same thing. Okay, and then I would just have different age classes out here. But when I got to thinking about this and some of the questions that were being asked of me, again, I always back up to my ecological roots, think of how these ecological processes work, how individual tree physiology works, and how do we fit management into that. So we have a natural ecosystem, and the mountains topography makes that ecosystem a bit more complicated. I think Greg mentioned growing loblolly pine down in Georgia on a 30-year rotation, okay? And they were growing it to 30 years because within 30 years they can grow a 20-inch loblolly pine down there, which produces a saw log and a pulp log, and so they're on a 30-year rotation. The scary thing is if you go down to Brazil, they're growing genetically selected loblolly pine on a 17-year rotation, truly like corn or sugar cane. So every 17 years, it's just a big agricultural center with a sawmill and pulp mill in the center. And all around it, they've got these different blocks at different ages, and so that way they have enough fiber to keep their mill running every year. Well, here's a system we're dealing with, where we have differences due to sun hitting a south slope versus a north slope. We have a different natural history, places where fire burned differently on the landscape, which it does, particularly in the mountains of Montana. North slopes have more moisture because the sun doesn't cook the moisture off of them. So they're denser. And when they burn as stand replacing patches. South slopes are hotter, drier, tree growth is slower, less fuel accumulation, so historically they tended to burn more as an understory type of fire. Again, very simplified, but this varies a lot in the wrinkles on the landscape. And based on when past historical disturbances happened, you have different species and different age groups across that landscape. And so how on earth do you figure out what can I cut, what can I cut, what do I want to leave? Throw in on there grizzly bear habitat and lynx habitat and fisheries habitat and water protection. And you know, one of the first things that I always mention to folks when I started out in a teaching capacity is I always heard this mantra, well, it's not rocket science, you know, it's just forestry. And I said, no, it isn't rocket science. It's actually more complicated. Because you think of the most complex thing we've built, which might be an F-22 fighter or the space shuttle, I always throw out there. You know, you got computers and circuits and aerodynamics and heat tiles and all that stuff. You look at a forest ecosystem, you have the tree species. You've got hundreds of understory species. A thimbleful of topsoil may contain as many as 80,000 microbial organisms, about 70% of which have not even been identified because they're weird. You grow them on one medium, like fungi, you grow them on one medium and they produce a certain structure. You grow them on a different medium, they produce another structure. Are those two different species or different growth forms? So it gets complicated in a hurry. And if you look on an acre of ground and you want to account for every organism that's on that acre, it's vastly more complicated than something like the space shuttle. The flip side is you don't need to know how a car is built to drive it. Okay? You just need to know the basic principles. And so these 5 things are really going to take this apart in a way that makes it a little easier to look at that complexity of interactions that's out there, that gives you a little bit more security that what you're shooting for, what your management objective is something that you can achieve. So number 1 question that comes to mind when you're, okay, I just bought 10 acres or 100 acres or whatever you can afford, and believe me, I feel your pain. The 20 acres I have, I didn't inherit money. This wasn't given to me. I'm paying a mortgage on it, and that's about 60% of my paycheck goes into paying off my property. And I've managed it such a way that as soon as I got it paid off, I get to pay tuition for my kids. So, you know, there is this cost in ownership, and so you want to make sure you're getting it right. So, number 1, what tree species, and you can modify that, understory species occupies your site? In this case, this is eastern Montana. This is ponderosa pine with blue bunch wheatgrass, Idaho fescue underneath, and a variety of different forbs that play different roles. I mean, who's familiar with lupins, for example? a nice blue flower, cone-shaped flower. You know that lupins can put as much as 40 pounds of nitrogen per acre per year as a nitrogen-fixing plant into your soil, which in turn is the only source of nitrogen for the trees to use on that soil. Okay, so these types of things play an important role. What do you have out there? So first step, get out there and figure out what you got going there. Is it a noxious weed? Is it a native plant? How much of it is there? Why is it there? Is it responding to disturbance or lack of disturbance? And kind of along those lines, particularly in Montana, where a lot of places we're dealing with multiple tree species, but here as well, is question sort of 1B is what tree species can occupy the site? So I may have ponderosa pine there now, but will quaking aspen grow there? Can it grow there? Okay, there's some guidelines, there's information, where if you look at the understory plants, if you have certain water-loving plants that are commonly associated with aspen groves, then you know that the site may support aspen. On the other hand, if you don't have those, and you go out, spend all your money to plant aspen or spruce on the site, and it can't make it there, you just wasted your time. So there's a difference between what's there and what could be there. And so, like in Montana, a lot of places, ponderosa pine is a pioneer species. Douglas fir, grand fir, something else will move in over time. Is that something we want to see happen or not see happen? Number 2, what is the age distribution of the trees on the site? Okay, this can play an enormous role on the overall health of your forest as affected by wildfires and insects and disease. So certainly with ponderosa pine in Montana, there's been a lot of research, and I'm sure you hear the same thing here in the Black Hills on ponderosa pine, that this species evolves and needs and will only get big and old if you have frequent surface fires. Okay, this is a place called Prims Meadow north of Missoula. These ponderosa pine trees are 550 years old. They're 4 feet in diameter, and they developed during that period of time with frequent fires. However, they're growing on a subalpine fir site. They actually shouldn't be there. The reason they are there in that capacity is this was a favorite camping site of various Native American tribes that moved through the area, and there's all sorts of evidence that has proved to that. And we can take that a step further, that actually the frequent fire ponderosa pine ecosystem, at least in Montana, was probably 80% created by frequent Native American burning. They move into an area, they leave out, they light it on fire. This is a common practice. You read any of the historic journals, Eye of the Needle by Jack Nisbet about David Thompson, who was a famous explorer that came through Canada down into Montana before Lewis and Clark came through this country. And he documented what was going on out there. And so Native Americans had a huge influence on forest development. If you're going to wait for lightning to give you a fire every 5 to 10 years, you may be waiting a while, because it's pretty fickle where that lightning's going to start a fire. So many of these big old ponderosa pine forests were created by human activity. And so what's considered natural by some, saying, well, look at this, you know, all of our forests should look like that. Well, if you want them all to look like that, you're going to have to manage the daylights out of them to get that, to keep other species from crowding in and creating fire hazards so that you have a standard placing fire instead of a surface fire. Over time, all forests are dynamic. So you may look at a site, in this case, where it's an uneven age. You got older trees, you got younger trees, you have multiple age classes on a site. And there's value in that, but there's the other part of the distribution of those on the landscape. This is largely a Douglas fir forest in Montana, and we had a spruce budworm outbreak on Douglas fir. It's a defoliating caterpillar. Eats all the foliage off it, only eats the new needles. So it has to be on the area for 5 years to kill the trees, but it also will go along with Douglas fir beetle that acts very much like mountain pine beetle. Okay, the beetles bore under the bark. The larvae take a year to grow. They emerge in the summer, and then they hit other big trees. And Doug fir beetle will only hit large diameter Douglas fir. So we had an outbreak that started out as 500 acres, and in 3 years it blew up to 50,000 acres in the Bitterroot Valley. So this is a managed landscape, a controversial one. Every management on national forest in Montana is controversial because we have groups that don't want to see forest management. But you notice up on top there's that strip clear cut that was put in that's regenerating. To ponderosa pine, by the way. So I took this picture in 2005, and I came back in 2006, and that's what it looked like. In 1 year, this is what Doug fir beetle did. And we see this over and over. The only part on that landscape that's green is that old clear cut with the 20-year-old trees in it, because the mountain pine beetle or the Doug fir beetle isn't interested in those young trees. It can't make a living in them. The bark's too thin. So the diversity in this case, the age class differentiation, helps keep this ecosystem healthy. Now, bark beetles are a natural part of an ecosystem. They kill trees. There's woodpeckers and bark cleaners that eat the larvae, and they need them for a living. So some level of bark beetle activity is pretty typical. But nature doesn't always work on a steady state basis. It works on a boom and bust cycle quite often. In the Black Hills, you're in a bust cycle right now with mountain pine beetle just going rampant in here. But if you came to the Black Hills probably 100 years ago or 200 years ago, you would not see the vast density of trees you see now either. So things flow and ebb with all sorts of different processes that are going on. The thing is, when you have bark beetles hit an area, you got a lot of dead trees. This happens to be lodgepole pine that was hit by mountain pine beetle. And all you need is a spark in there, and you're going to have the fire from heck burning through this. And that goes along with it. Versus, say, here where we have multiple age class. This was also lodgepole pine, where a harvest unit was put in here. 90% of the mature trees have been killed. This is one of those green patches on the landscape. And it gets better because this green patch is not only with young trees available, but not interesting to bark beetles, it won't burn very well either. And I'll show you some more examples of that. So age class diversity is important, but sometimes when you have a big tree next to a little tree, both the trees are the same age, because one is very suppressed, it's not getting the light and water it needs to grow, and the other one is basically hogging it all. It may be genetics involved in there. I mean, any farmer, rancher knows that you have X number of calves or pigs or whatever, you're going to have some that are big and some that are small. Same thing happens in trees. So, you know, are those truly different to a young tree and an old tree? Are those both old trees? One's suppressed, one's growing well. So, right along with that, what is the density of trees on the site? And density and age sometimes goes along together. So in the background, we've got about 600 trees per acre. In the foreground, we got 50 trees per acre from a harvest unit that was done for commercial purposes, for wood fiber. Here we have, you know, the opposite of that. What's commonly referred to as a dog hair thicket. Now, is that good? Who would think that, hey, I look at that harvest and those trees left that, is that good? Who says it's good? Oh, come on. Who says it's bad? Come on, there's got to be somebody, okay? If this were my property, this would suck. I would not want this on my property because I don't want to see my neighbor's house, okay? This is too much for me. The core question is, what are your objectives as a landowner? Okay, if I'm an industry forester and I needed to supply my mill with wood, what I did here is a modified seed tree cut. Within 5 years, I'm going to have lots of little trees growing in there versus that uniform stand of dog hair stuff behind there. And the flip side is, within a couple of years, in the spring, I'm going to have the elk and deer out here because this is the only place where there's something to eat. But come fall, when everybody's running around with a rifle, this is where the elk and the deer are going to be, because if they're out there in the open, they're going to get killed. So, you know, there's no good, there's no bad. It's a question of, is it meeting your objectives as a landowner? And so, what species do I have? Okay, this is a mixture of ponderosa pine, Doug fir, and lodgepole pine. These trees, surprisingly, are 70 years old. They're stagnant. None of them has enough to grow. They're just barely staying alive. Okay, so what do I want to do with them? And I've got, in this little thing, probably closer to 1,000 stems per acre. Okay, does that meet my objectives? This is why in your management plan, we'll go back to that, what are your objectives? What do you want out of your forest? If you want grazing and you want wildlife, maybe you want to have a little bit of both. Good question, sir.
Well, this brings up a question that's in my mind all the time. I walk the forest a lot. Every time I see something like this, I think about the areas that they've made into wilderness areas.
Right.
And I can't imagine how that can be a profitable thing for the country when it creates a big fire hazard and things like this. Would you comment on that?
Sure. Most wilderness areas in my neck of the woods, Northern Rockies, are put in places that maybe timber management isn't the best utilization for. It's high elevation areas, takes trees a long time to establish, a long time to grow, soils are thin, they're erosive. Now, there are areas that are very productive for tree growth that are also wilderness areas. I mean, Yellowstone National Park is a de facto wilderness area because no management is allowed in it. The value in those is, and we go back to that movie of 24 hours of airline travel. There are a few places in the world that have places that you might call wilderness, where by definition untrammeled by human activity. And over time already, the worst thing you can do to protect a piece of ground is call it a wilderness area because everybody wants to go there. So by designated as a wilderness, you're doing the opposite of what you really want to do, is keep people out of it. But we're one of the few countries, one of the few last places in the world where you have some larger chunks of ground where you can go into and pretend that you're 200 years into history. Now, is that good or bad for the landscape? It's neither, because nature is very resilient. And without question, and I'll show you some graphs and charts of that, without question, these landscapes that we know as forested lands, historically, at some point in time, in the last 10,000 years, since the last ice age, did not have forest on them. And then they had forest on them, and then the whole thing burned down. And it wasn't forest for a while. And then trees slowly came back. Things are always changing out here. We as humans hate change because, we just get comfortable with something. But change is going to happen one way or the other. Now, do I feel good about, say, if Montana, we get more wilderness, and that causes more mills to shut down, and that reduces our rural communities into a state of poverty because there's no work, it's 80% federal land, and there's no economic opportunities for the people that live there? No, I don't agree with that. I like multiple use, but there is a space for wilderness. It has to be done thoughtfully and carefully. There is a space for multiple use. There is a space for industrial managed forest. I mean, the demands of the population of the world these days on our natural resources are above the carrying capacity already. We've got a lot of people that are starving out there. We have too many people, and we can't feed them all. So those are, and we're just continuing to grow. So these are all things that play into this, because land management and forest management is ultimately a social decision. What do people want to see there? And is it a place that's valuable to society? In 100 years from now, Black Hills, Montana, all these wilderness areas, you're going to have to put in a permit, a lottery, to be able to go backpacking there. It's already happened for major rivers. Think of the Salmon River. 30 years ago, anybody could raft the Salmon River through a wild, primitive area in Idaho. Now, to raft the Middle Fork, if you apply every year for a permit, your odds are that once in 40 years you'll be drawn to raft that river. Think about that, So, these are the signs of the times and the way things are. Do I agree with every wilderness? No. Do I think there should be more wilderness areas? Yes. In specific places where a thoughtful process has gone in place and said, hey, yeah, this is a good thing to do. So that'll teach you for asking me a question, huh? The easy answer is it's complicated, and it is. But anyways, all right, so onwards, density. So why is really, I put this diagram together because when we talk about density in trees, really it's all about limiting factors. If you garden, you know you got to thin your carrots or you have lots of little carrots instead of big carrots. Same thing in forestry, the biggest limiting factor we're dealing with in western forests is water. So, for example, this little illustration I put together to make a point is if you take a ponderosa pine tree that's 20 feet tall, it's going to have an average lateral rooting distance of 10 feet. It's going to have a root depth of about 4 feet. And on an 80-degree day, 30% relative humidity, low humidity sucks the moisture out of a tree. It basically calculates out to a suction of about 200 pounds per square inch. That tree, and ponderosa pine is very water conservative, will lose about 10 gallons of water in one day. Okay? So where does it get its water from? Well, the soil, water doesn't move easily through soil. It moves downwards because of gravity, but it doesn't move laterally really well. Okay? So when you think of where that tree gets its water from, it's basically from the root volume or the soil volume that its roots occupy. So in this case, if you have a cylinder with a radius of 10 feet, a depth of 4 feet, that's basically a soil volume of that cylinder is 1,256 cubic feet. That's a lot of soil. That's a big pot, basically. But when you look at a typical silty loam, a cubic foot of soil will hold about a pint of water times 1,256 cubic feet, 8 pints per gallon. So that's 157 gallons of water that tree has to operate from in that big soil volume. Okay? You add more water to that soil, it goes through. Okay? Water can only hold so much, or soil can only hold so much water, just like a sponge. Well, if it's using 10 gallons of water a day, how many days worth of water does that tree have? 16 days, basically, right? That's not a lot of days of water. And that's that tree going full bore, full photosynthesis, good energy production. Okay? Now, what if there's 2 trees in that soil volume? The tree has 7 days worth of water. Okay? What if there's 5 trees in that soil volume? So really, the concept of thinning and spacing trees is to give the tree's root system more soil to draw its water from. You're just making the pot bigger. How do you grow a bonsai tree? You keep it in a small pot. Okay? So next time you're out there hiking and you see these little ponderosa pine trees and you age them with an increment core or cut one down or however, whatever you're allowed to do on there, and you count the rings on it and you say, good grief, that 2-inch diameter tree is 80 years old because it doesn't have enough water. So really what we're managing out here for is water, and density plays that role. And if you take this into an ecosystem or landscape level scale, now again, this is more of a Montana diagram where our typical, what we call succession is bare ground gets colonized by a pioneer tree species, which in our case is ponderosa pine. It can tolerate hot, dry conditions. Once it occupies a site, then Douglas fir or grand fir typically moves in underneath it. It's more shade tolerant, so it can regenerate in the shade. And to get water, it's not going to want to compete with ponderosa pine that's very deep-rooted to find water in rock fissures. It's going to get that water from the shallow soil surface. When it rains, it's going to grab the water before it gets to the ponderosa pine. So it has a shallow root system. But the other part of that is when you have both shade-tolerant and shade-intolerant tree species, ponderosa pine, Douglas fir. And by the way, one of the things I've noticed in Black Hills is your ponderosa pine tends to be more shade-tolerant than ours does. You get regeneration under dense stands of trees that just would not happen in Montana. So, your ponderosa pine is 2 needles, ours is 3 needles, so that's an adaptation as well, perhaps making it more shade tolerant, who knows. The point is that as a forest gets denser, the leaf area increases. And leaf area index is one of those things we use. It's basically, leaf area index is a projection of how many square feet of needles is above a square foot of soil. Okay? The soil absorbs water by surface area. Okay? So every square foot of soil absorbs a certain amount of water. Well, if I got 3 square feet of needles over that soil surface, it's a leaf area index of 3. If I have a leaf area index of 8, I'll have 8 layers of leaves over that square foot of soil. With every increase in square foot of leaf area, you're doubling your water consumption because those needles are transpiring water out of them. Okay? So as this forest gets denser and denser, our leaf area index goes perhaps from 3 to places in Montana, we get leaf area indexes of 8, which means the water evaporation It doubles every time you get that increase in leaf area. But it gets worse. Not only are the trees sucking more water faster out of the soil, when it rains or snows, who's ever noticed that when you walk under a dense forest canopy, the snowpack's not so deep? Okay? Because those leaves and that leaf area intercepts rain and snow. And when that snow and rain hangs up in the needles, it evaporates right back there, never makes in the soil, and the trees can never get it. So you ever wonder why ponderosa pine starts and prairie ends and trees start? In Montana, it's rainfall. Our prairie ecosystems on average get about 12 inches of rainfall per year. We don't get trees until we get at least 16 inches of rainfall per year out there. Okay? So our trees here start at 16 inches, or actually with Douglas fir, more like 20 inches of precipitation a year. Once we get that dense leaf area, half the water gets hung up in the canopy and it evaporates right back out. So not only do we have greater demand for water by those trees, we're getting less in the soil, sometimes half of it, and now we have a forest growing in a 10-inch precipitation zone. Trees are all water stressed, perfect food for bark beetles, perfect for wildfire to burn up. And the wildfire nukes the whole thing, and boom, you start out from the beginning again. And this is the natural cycle of things, if you want to call it natural or not. Now, management, you can go in here and you can moderate this. I can thin it. I can reduce water use. I can selectively decide which species I want to grow there. So, by the way, birches use a lot of water. Quaking aspens use very little water. Cottonwoods are your real water hogs. If they can, at that 80 degrees Fahrenheit, 30% relative humidity, they'll go through 100 gallons of water a day, a big old cottonwood tree. So really, forestry, in many circumstances, comes down to managing soil water. That's what you're doing by spacing the trees and deciding which trees you leave. So little trees, really, the reason they can be closer together is they have a fraction of the leaf area as the big trees. So it's all, there is a light competition factor in there too, but water will get them first. So thinning, there are many rules for thinning. It's really site dependent and dependent on your tree species. So, here we're at about a 10 to 15 foot spacing. Okay, here's more like a 15 to 20 foot spacing. Here's a 20 to 30 foot spacing. It all depends on what your objectives are. If I want to grow grass, this is what I'm going to be shooting for, but I'm also going to be getting a lot more regeneration because now there's water available for seedlings. There's light available for seedlings. So by manipulating density, you're manipulating what can grow based on water availability on the site. And water availability, at least in Montana. Now, John is the expert on mountain pine beetle here in the Black Hills, and just in discussion with him, things seem to work a little differently here than they do in Montana. But thinning does have a really good impact on mountain pine beetle, and this projector doesn't show color real well, but this thinned area in the front is pretty green, and the dense area on the back is pretty gray on my computer screen and on the actual picture. And it's all, the trees up front have more water, and it's a more hostile environment for bark beetles. They're in the sunlight, and they get hot more, they dry out faster. So there are other implications in there. If I do want regeneration, if I only have one age class of trees, there's an issue there. It's not quite as resilient. So maybe I want to do things like group openings, wider spacing. But always be careful what you wish for, because if you want regeneration, sometimes either you don't get it or you get it with a vengeance. And the Black Hills here, there's a real strong correlation between weather events or climate events and regeneration. You only get regenerations when you have a wet summer, basically. When you have a dry summer, they germinate, but then they die because they run out of water. Thinning isn't necessarily the silver bullet either. Just a second here. This is, again, not shown up real well, but this was a heavily thinned ponderosa pine stand. It did help with mountain pine beetle, but still about 20% of these trees got hit. It also depends on how many beetles do you have. If you got 1 billion of them coming off the mountainside next to you, no matter what you do, they may get hit. There's just too many of them. Question?
Can you explain that we have a lot of white spruce coming in underneath ponderosa pine, several ponderosa pine stands in the Black Hills? Probably historically wouldn't happen. What's the impact of the spruce on our ponderosa pine stands, and is it good or bad, or like you talk about, it is both?
Well, again, depends on your objectives. Really, to go back to address that, I got to go back to this diagram. This is the same thing, where the white spruce doesn't tolerate, shade tolerant, shade intolerant is really the wrong thing. It should be sun tolerant versus non-sun tolerant, because for photosynthesis to occur, it really maxes out on our native trees and our native C3 plants here at about half full sunlight. More than that, it's too much energy. And the needles heat up, and when they're hot, they lose water at a much faster rate. Okay? So the whole trick is to stay cool. Ponderosa pine has those long, wispy needles because it helps them stay closer to air temperature. Without that, needles can easily get up to 140 degrees, 150 degrees Fahrenheit, which is pretty hard on them. So spruce comes in just like Douglas fir, playing the same role. Short, stubby needles. It overheats too easily as a young seedling. It doesn't have the root system to get enough water, so it's coming in underneath the ponderosa pine because it's shady and cooler there, which allows the seedlings to germinate. It's slightly more shade tolerant than ponderosa pine, which is why it comes in more prolifically than ponderosa pine does. The downside is it uses more water, and that understory will steal water from the overstory trees. So you're going to get into a situation where your leaf area is probably too big for the carrying capacity of water resupply for the site. And so, spruce is a fine tree. It grows well, it grows fast in the right conditions. But when you have something that's doubling the leaf area, you got to manage that and say, okay, I got too much leaf area, what do I want? Do I want the spruce? Do I want the ponderosa pine? The spruce as a juvenile needs shade because that soil surface gets hot. And the closer those leaves are to the soil surface, again, the more water they're going to lose. So once it gets up to a certain size, it can stay cooler because it's in the airflow. Then it can be released if it can actually grow on that site. And species ranges change. And let me complete addressing that later on. Otherwise, I'm going to run out of time here. So question 4, what's the condition of the tree crowns on the site? Okay, so now we're going to get a little bit more into the physiology. Why is crown important on a tree? So we already talked a little bit about physiology, but basically the way a tree works, like any other plant, is the only place where energy production occurs is in the leaves of the needles, photosynthesis. Okay, the leaves are unique organs designed to absorb carbon dioxide from the air and use the sun's energy to convert that carbon dioxide into sugar. And sugar is the basic building block of everything else. It feeds the tree, it builds cellulose. Cellulose is just a sugar polymer. That's all it is. Okay, so this stuff. And for it to absorb carbon dioxide, it has little pores on its needles called stomates. To absorb carbon dioxide, the stomates have to be open. The problem is that water molecules are smaller than carbon dioxide, so for every carbon dioxide molecule that a tree absorbs, it loses about 1.5 water molecules. So water extraction is faster than carbon dioxide input, and whenever the humidity is lower than 100%, the trees are going to lose water, and the lower it gets, the higher that suction of that dry air on pulling water out of the tree. Okay, so there's a trade-off. Trees either starve to death or they die of thirst. Okay, if they can close those stomates to prevent water loss, but then they can't absorb carbon dioxide and produce sugar. If they open the stomates to produce sugar, they lose water at a phenomenal rate and they start dying of thirst. So trees have this careful balance. Usually photosynthesis is highest in the morning and it's very low in the evening because they shut down their water loss because the humidity is the lowest in the afternoon. So you think, okay, if I need lots of water, I'm going to grow a big root system. And trees get water from either surface water or deep water sources. The bigger the root system, the more water I get. So every tree growing on a dry site ought to have this enormous root system, right? But the root system has to be fed. It's alive. It needs sugar. So the bigger the root system, the more sugar is needed, the bigger the leaf area you need to supply the root system with sugar. So every tree is a very delicate, I guess I didn't have that on here. It's a very delicate balance between leaf area and root system. And it's balanced between water availability and water demand and sugar production. So as a rule of thumb, and all rule of thumbs are inherently wrong, but they give a general concept. As a rule of thumb, the root area of a tree is going to be about equivalent in size to the leaf area of the tree, okay? Because that root system is needed to supply with water, the leaf area is needed to keep the root system alive with sugar, okay? The stem and the branches are infrastructure. Their only purpose is to position the leaves in a place where they can do their thing, okay? and that stem is also alive and needs sugar. So think of a tree as the ultimate corporation. The leaves are the workers. They're producing the widgets. The branches, the stem is infrastructure. The roots are shipping and receiving. Okay? What happens when a company starts getting more and more supervisors compared to workers? Okay? So as a tree gets bigger, that stem are the more supervisors. The tree gets bigger, it becomes less and less and less efficient because you have more stem that's needing that sugar, and the leaf area, once the tree reaches a certain size, the leaf area doesn't necessarily get bigger. So essentially, trees, the bigger they get, the older they get, the more they become like General Motors. They got too many bosses and not enough workers, and when a tree stops making a profit, which is sugar, what's the last part of the tree to get the sugar? The part that's farthest away from the needles, the fine roots, the root tips. What's the part of the tree that supplies most of the water? The fine roots and the root tips. So when the tree goes into energy stress, the roots start to die back. Less water production. Less water production, less photosynthesis, less energy production, roots die back. When there isn't enough water, what's the last part of the tree that gets water? Furthest part away, the tippy top. The top dies back. Roots die back, top dies back. I call it the death spiral. You can observe it in some of these big old trees. You see some top mortality, and next year a little bit more top mortality. What you're not seeing is the roots are dying back as well. Or you go into a drought situation where there's less water available. And once that tree gets out of balance, then it starts slowly declining and it's gone. So physiologically, the bigger a tree is, the less efficient it is. The most efficient trees are the younger trees that have a much higher worker ratio to infrastructure ratio. Okay? And that's, to pass that on, the stem of a tree, the part that grows is the cambium. You got all these different layers, okay? The only part that's actively growing on a stem is that cambium layer. It's between the bark and the wood. And every spring and summer, it grows a layer to the outside and the inside. What it grows to the outside, what's called the outer bark, the phloem, the inner bark as well, its purpose is to transport sugar from those needles down to the stem and the root system. Okay? And because transporting sugar, whenever you squeeze syrup out of a bottle, the smaller the hole, the harder it is to squeeze syrup, right? That phloem tissue is made of very large diameter cells that are structurally unsound. So after 1 year, those cells collapse and they get pushed to the outside, and that forms the outer bark. So look at ponderosa pine bark. You'll see the layers. Each of those layers is collapsed inner bark. Okay? So that's the feeding part. Now, the inside, that cambium also grows a layer of wood to the inside. The purpose of the sapwood is to transport water from the root system up to the needles. So you got two different plumbing going two different ways in that tree. And the layers in there is springwood and summerwood. Okay, trees don't grow in the winter. It's too cold for the chemical reactions to occur. So that the low density wood that transports water better is the white wood. The high density wood later in the summer that doesn't transport as much water is the dark wood on there. And then those are the rings that you count on there. The sapwood is alive. Okay, so that's an energy drain on the tree. It has to feed it. A tree only needs so much plumbing to supply itself with water, and so the sapwood is usually a pretty good ratio to the crown area on the tree too. So when the tree no longer needs that old sapwood, it will let it die. That's what forms the heartwood. That's dead. The reason the heartwood is a different color is because trees don't go to the bathroom the way you and I do. They deposit their waste material in the dying cell tissues of the heartwood. And that waste material is sometimes toxic stuff. Okay? It's waste to the tree, and it's poisonous, and that's why the heartwood shows greater decay resistance. When you see a tree die and it starts to rot, the sapwood goes first because it's full of sugar. It's nutritious to things like the flathead borers and roundhead borers and things like that. Nothing attacks the heartwood because it has no sugar and starch in it, but it also has toxins in it, like redwood. Okay? Redwood is so decay resistant because the wood has specific terpenes and phenolics in there that are really nasty. And nothing can eat it, and that's why you make decking out of redwood. Incidentally, who's bought redwood any time in the past? It's very expensive, isn't it? Was it all red or was some of it white? Good, you're getting the good stuff. Nowadays, because it's hard to cut old growth redwood, because trees usually don't form heartwood until they're older, what you get is redwood sold, but it's the sapwood that does not have those toxins in it. And guess what? It's not any more decay resistant than anything else that you buy out there. It has to be the heartwood that has those things in there. So Anyway, so just a little bit of tree physiology, but you know, how these trees function is part of understanding how the forest works. So when we go back to crowns, you know, this category, why are crowns important? Well, we want crowns that typically have a ratio that shows enough leaf area to keep the tree healthy. That means not only alive, growing, but enough excess energy to produce defense chemicals. Ever wonder why some of those trees out there, everything else is getting hit by mountain pine beetle, but they don't like that particular tree? Okay? Well, we wonder the same thing. We're not quite sure. It might be that that tree is getting more water than the other trees and therefore has enough energy, surplus energy, to produce defense chemicals that the beetles don't like. It could be that there's a genetic characteristic in the tree that it's just producing a certain type of defense chemical that the beetles don't like. It might just be chance that, you know, in their confusion of pheromones and flying around, they just missed that tree. So a lot of different things. But in general, some rules that we found is the trees that are physiologically the most active, photosynthesizing the most, producing the most excess sugar, also have the energy to produce defense chemicals. And so those are 1s and 2s. 30% of the total height of the tree, if it's in crown, that's probably a pretty good tree, probably. Okay? Now, the difference between a 1, 2, and a 3 is simply that 3 is flat-topped. Now, flat-top means the tree has reached its maximum height. And the maximum height is determined how far and how fast it can transport water. Trees operate on a suction principle, and you can only suck water so high. If your well is too deep, you need a pusher pump. Same works with trees. And I think the maximum height that's physically possible is about 215 feet. Okay? And interesting, the tallest tree is a redwood on the coast of California that's actually grown to about 220 feet. And so it's a big mystery amongst tree physiologists. How can that thing transport water 10 feet higher than the principles of physics ought to allow it to transport water? And it might be because it's foggy and they're absorbing water some different way. But that's aside from the point. The point here is that for every site, trees can only get so tall and they can't transport water. And out here, trees are shorter because transporting water from the soil to the top, there's a delay. And if the evaporative demand is too high, is faster than the water resupply, that tree will grow a shoot high and that shoot will die from drought stress during the summer. And when that consistently happens, the tree isn't pointing anymore, it starts to grow sideways and you get the flat top. Okay? That's maximum height potential. Typically you find that with old trees. So 3 would be an old growth tree. Well, when we're selecting trees to leave in a forest, we're making decisions. Do I take this one? Do I take that one? I'm trying to space them out. What you really want to be looking at is the crowns of trees. Those that have good crowns, 30% or more, have a high potential for 1, growing bigger, and 2, living longer. Those are the 2 caveats when we're leaving a tree. If we leave it, we want it to live and we want it to grow, right? Number 3 isn't going to grow a whole lot. But trees can persist with a good crown that's flat top in that slow growth phase for hundreds of years. So 3 is a good one to leave because it has a good chance of staying alive out there, if it has a good crown. The opposite of a 3 would be a 7. Okay? It's flat-topped, and flat-top, the reason flat-top is important is if we have a tree that has a small crown. Let's look at 5 versus 7 on there. Okay? 5 has too small a crown. But because it's pointy, it has the potential to grow a bigger crown. Trees only grow crown upwards and somewhat outwards. Okay? So 5, if we leave it, has the potential of growing itself into a 2. 7, on the other hand, has reached its maximum height. It won't grow taller anymore. And if it's got too small a crown, it can't grow a bigger crown anymore. So it's stuck. It's stuck with too small a photosynthetic area, and it will remain a weak tree. So in our selection criteria, 7 has a greater probability of dying relatively soon than 5. 5 has a greater probability of dying than 2 because, number 1, 5 is a tree that grows in a suppressed type of scenario. It's got an itty-bitty crown, it's narrow, there's a chance of bending over or breaking over, but also it's not producing enough energy to keep its infrastructure, its stem, alive. But it has the potential to grow into a 2. And that's why we have this ranking system in there based on crown. Doesn't matter what species you're looking at. okay? So when you're deciding to leave a tree, a 1, 2, and 3 ensures you the best chance that your tree will survive for a longer period of time and will continue to grow well. A 4 or 5, it can recover. It's a weak tree, but it can recover. Okay, 6 is a real interesting phenomenon. 7 is a definite it goes. 6 is where the top's been killed by ips or a porcupine. Okay, interesting thing, and this is an opinion. Okay, it's not a scientific proven fact through data and analysis. I see an awful lot of ponderosa pines that have U-shaped tops. Okay, different than a V-shaped top. Okay, it's a U-shaped top, which indicates the top has died out of it. And I see a lot of that, a high proportion of those, not being attacked by mountain pine beetle or western pine beetle in Montana or ips. And there's this interesting theory in tree physiology. It's called the grow or defend theory. And it's been shown to some level that trees that are wounded go into defensive mode. That is, they shift their carbohydrate production from growth to defense mechanism. And it seems that to some degree that may be going on ponderosa pine, even on my own property. I've had some trees top killed by ips, and western pine beetle, mountain pine beetle has avoided those. But they've hit the fastest growing ponderosa pine trees because they have a high sugar content. So and this varies from site to site, genetics, water, all these types of things. Again, when I compare notes with John and other people who study mountain pine beetle, they're finding different things out here than I'm finding. So there's a lot of things affecting whether a tree gets hit by mountain pine beetle. We were just talking about this the other day. There is no single silver bullet. So one tree may be more nutritious to a beetle. The other one may not have enough nutrition to it. One might be suddenly drought stressed. The other might have lots of water and is producing lots of sugar, and so the beetles like it. So there's all of these trade-offs that occur out there. So sometimes a 6 might be an okay tree to leave. It's not going to grow well, but it may survive. Versus an 8. An 8 is a sign of root disease or root injury. Conifers will typically hold their needles for 3 to 7 years. 5 is an average. Those are the inner needles. The older the needles get, the less efficient they get because the pores get plugged with wax. When a tree gets really stressed, the first thing it'll do is drop all of its older needles. It makes a tree look very thin. Okay? It's a sign of root injury. It's not getting enough water. Typically, when you're seeing a tree get to an 8 stage, it's about ready to die on you, and it's a good time to take it out. Okay, so again, the scale is designed as a relative measure. As the higher the number, the greater the likelihood that the tree will be dying at some time in the future, so that's a good tree to take. The closer you are to a 1, 2, or 3, the better chance that that tree will live for a long time. And here's some examples. This is Douglas fir. Okay, so left is a really healthy crown. Far right, it's starting to decline a little bit, and the one in the center has serious problems. Now, this is artificially created because they put a paved road and a sidewalk next to these trees, and they really messed up their root systems. So the one in the center got hit the hardest. The one on the right got hit pretty hard. So the one in the center died within 3 years of this. Okay, it's dead. The one on the right side is about ready to go out. It's persisted for about 10 years. The one on the left is doing just fine. And this is pretty much an indicator of root system. But when you get in a forest situation, there's all sorts of things to look at. So these are ones, sort of. They're 50% or more crown. So they're good trees to leave for longevity, sort of. They actually have too much leaf area. They can suffer from water stress because they have so much needle area, they got to keep it alive. And it makes a pretty darn bad board if you're growing trees for wood because all the knots in it. So, but, you know, those are good ones to leave. Now we get into this situation. Oh gosh, what do I take? What do I leave? So we got a ponderosa pine. I don't know if you can't point at this in here. We got a ponderosa pine right here above me. It has about what we call a 10% crown. It's very thin. If I give that tree more space, it won't know what to do with it because its crown is a reflection of its root system. And it's going to sit there for a long time, regrowing a root system and starting to grow a crown. It can eventually recover. Chances are, if I give it too much space, though, it's going to bend over or break off on me. So crowns are very, very important. So here's, a thinning that was done. Those are on the scale that was there, probably closer to a 5 or something like that. Very thin, showing they were very dense. These trees will recover if a big windstorm or heavy snowstorm doesn't break them off. So lots of things to look at. yeah, not so good. Okay, they may recover if they survive the next 3-4 years. Good chance they'll probably die or break off, or beetles will get into them, because they were growing in a very dense stand. This whole situation has changed now, where the roots used to stay cool because of this shading. Now the roots are being subjected to full sun. The soil surface temperature that used to max out at 75 degrees is now getting up to 140 degrees, 150 degrees. It's pushing the water down. So here's another rule is don't change site conditions too radically all at once, because the trees need time to adjust to them. And you know, finally, I throw this one here. The one on the right side, again, this is a funky projector. It's actually orange. The beetles have hit it and killed it. Sometimes the best tree you leave behind there is going to get hammered. You did everything right, and the beetles still hit it. Okay? There are no silver bullets. This one might have been, we could speculate, was putting all of its energy into growth. It was full of sugar, very vigorous, and wasn't putting anything into defense. And there is evidence that nitrogen fertilizer on ponderosa pines is pretty deadly, that it makes the tree much more susceptible to mountain pine beetle. At least in the northern Rockies it does. And the theory is that the trees are nitrogen deficient. When you give it lots of nitrogen, it's kind of like giving a 5-year-old kid a half-pound bar of chocolate at 10 o'clock at night. It just goes, yeah! And, you know, its carbon balance gets out of whack and becomes super susceptible to mountain pine beetle, because it's going, hey, it's a sugar tree. Lots of energy and no defense. Finally, 5, what is the distribution of tree species, ages, and densities across the site or the landscape? Now we get back to the accumulation of 1, 2, 3, 4, and 5. What species do you have? What age classes do you have? What density do you have that tells you what stress levels there are for your different age classes? And what's the distribution across the landscape? Because that will determine when you do have something like mountain pine beetle or Doug fir beetle or wildfire or spruce budworm, at what magnitude will it impact the landscape? So here is what, you know, got a lot of environmentalism going, these geometric clear cuts on the landscape. Again, the projector isn't showing it real well, but all the big trees are gray because they're very susceptible, in this case, to Doug fir beetle, and all the regeneration, the green clear cuts are the only thing that's green out there. So, you know, back to the wilderness question, all these other questions. What is a healthy forest, or what is a healthy forest ecosystem? It's one that can sustain itself as forest when you have ecological fluctuations occur, like catastrophic mountain pine beetle, like catastrophic wildfire. And the more that your landscape is all the same age, the same species, the more any of those types of disasters will impact the landscape as a whole. The more that it's broken up into fragmented pieces, the more that those types of things will hit certain components of that, but not other components. So this is actually a very healthy ecosystem because at least half of it is staying alive and is impervious to the Doug fir beetle that's hitting it. Now, we can look at the same type of thing. Again, this is western Montana. The larch only regenerates where you had past wildfires. This is the Flathead Indian Reservation. Not a lot of management. There's a little, they're doing some up there, but the patches of larch on the right show you where past fires were. Okay, and so the larch moved in, and this is actually a pretty healthy landscape because when something hits it, it will only hit bits and pieces of it, not the whole thing. And that circle on the left was the Schley fire that I watched burn right off my front porch. And you look at the pattern with which it burned, hey, it burned about the same as the past fires. So it's pretty right in tune with what it's supposed to do, except that it cost $5 million to contain that sucker. Okay, so something's a little different here now all of a sudden. And those patch sizes of past disturbance will not be the same everywhere. So one of the key questions for forest ecologists, forest managers, property managers, if I'm going to create a patchy forest to increase its resilience to these disturbance processes, what patch size should I work with? And that's a pretty difficult question. It's going to be the patch size that works for you and your objectives, and then you got to always look what's around me. I have a good friend of mine who had 120 acres, and he bought it, and it was on a mountainside that was all old growth timber. And he it was all pretty decadent, had a lot of disease in it, a lot of insect issues developing in it. So he did a salvage harvest on his, did a real nice shelterwood harvest. And then the next thing you knew, he had every deer from the mountainside on his property because he was the only one growing browse for those white-tailed deers. Oh, and he just complained about that because he was trying to get some tree species going there, a white pine again that had been lost out of the system. The deer were just decimating it. He says, what do I do with all these deer out here? And I said, well, you've created a magnet for them because you're the only place that's producing forage in this 5,000-acre landscape right here. Well, Plum Creek owned the surrounding ground, and 10 years later, they hit their ground pretty hard, and then the black cat fire burned through all of it. And the next thing you knew, his 120 acres was the only dense patch of timber on that whole mountainside. And guess what? The deer loved it because it's only hiding cover. So he went from being a deer magnet because he had the only forage production to being a deer magnet because he had the only cover on that site. And the reason it didn't burn is because of the shelter wood that he had done on there that created a relatively fire-resilient landscape, and he had left the most fire-tolerant trees back there. So what would have been the better solution is if Plum Creek would have managed a little bit more patchy on the landscape, together with Forest Service on that, and then more of the landscape would have been that mosaic, and it would have dispersed the wildlife habitat more across the landscape. So what you do may have a huge impact on the landscape around you. And that's some of the things you got to look at out there. All right, I'm going to just skip through this real quick because fire is a real big part, and we talk about surface fire. That will leave trees alive, that will be beneficial by recycling nutrients, and in this case, fire is a good thing. And then we have stand replacing fire, where fire is a bad thing. But again, stand replacing fire is a natural component of these systems. It can start a regeneration phase. We're going to get younger trees. It's a question, really, what boils down to magnitude of what impact you have. Okay, so is it a good thing, a bad thing? This is lodgepole pine forest. It comes back with fire. The cones are serotinous or closed. The heat opens them up. And by now, this is a carpet of green regeneration. And in 110, 120 years, the same darn thing is going to happen again. That's the way this particular ecosystem functions. Does management play a role in it? It can. If you don't want a 10,000-acre black patch, all you have to do is break up the continuity of the fuel, and you will build some diversity into that system so that the whole thing won't be hit at the same time. And we call this the clear-cut effect. It's prevalent on every single fire across Montana, where we have these younger trees. Their live fuel moisture is a lot higher. A lot of water in those needles, and it takes too much energy for the fire to dry them out enough to where they combust. And so fire skips over them. Okay? Is that good or is it bad? Well, again, depends on your objectives. If your objective is to keep some forest on the landscape, then again, the more diversity you have on your landscape, the more patchy it is, the more patchy your disturbance processes will be. Some other evidence. Okay, this is a map of mountain pine beetle on a landscape. The pink is mountain pine beetle. What does that landscape look like? It's very uniform. And so we get big patches. We look at another map. Here, the mountain pine beetle outbreak is very fragmented. We look at that landscape. Guess what? It's been artificially fragmented by regeneration cuts in there. So what we've learned, of course, is irregular shapes are much more aesthetically pleasing, potentially better wildlife habitat than square clear cuts. How do we survey our boundaries? What's the shape of your property? Okay, mine's geometric in shape because we survey in squares. So some modification in there. Other benefits of creating patches. Okay, this is just out of Ekalaka, north of here. I was there last week looking over the fire situation. This is a landowner who had done some thinning and group selections. Again, it doesn't show up real well in this picture. Around this landowner, everything is black. Where he thinned it and created these openings, these trees have been scorched, but they'll live. You go back, doing even better, and this is right what it looks like right next to it. Now, a couple things here. Not only did he maintain some of his forest, but look at the recovery that's going on out here. That rainstorm that you guys got here that flooded everything and blew out culverts, it hit that area too. And where he had opened, the understory had responded to it prior to the fire. Okay, this isn't going to do any good if you do this right as the fire is approaching. And so he had an intact understory in his open area. And grass does just fine with fire. It burns the top off and it comes back greener than ever. So you note there's no erosion off of his property. And if you're a cattle rancher or you're grazing animals or you have wildlife, things like that, you have created not only a more resilient forest, you've created a more resilient understory because it resprouts back. You go back to where it was dense forest, and you'll see this on your own forest, where you have dense canopy, you don't have understory. And you have a duff layer that's that thick that will also burn off where all the roots are. So this is, same time, this is a recovery. And when that rainstorm hit, all of the ash came off this mountainside and went down in the bottom of the valley. And that's really bad because, one, the guy's house was down there and he got 3 foot of sediment up against the back side of his house from this. And secondly, that ash has all the nitrogen, phosphorus, and potassium that was released in the fire. That was the nutrient loading on that site, and it's now off the site. So when you have a whole landscape that looks like that, you're going to have trouble. And you're losing some of your productivity of the site, you're losing some of your diversity off the site. And the thing about ponderosa pine is it's not adapted to crown fires. When you have a crown fire go, there's no seed that survives, there's no trees that survive, so unless you plant it, you have just converted that landscape from ponderosa pine to something else. And if you don't hurry your butt up in here because you have no resprouters and you have no native grass seeds, guess what's going to be the first thing in there? Cheatgrass and exotic noxious weeds. So managing your forest and creating some more diversity isn't just about the trees, it's about the understory and the site productivity and the hydrologic balance on the site as well. Okay, so what's an underlying factor in all of this stuff? 5 minutes, I'll be through this. Well, who's heard about climate change? Okay, everybody's heard about climate change. There's 2 things in climate change, and they're lumped together, and it does everybody a disservice. One is, what's causing climate change? Is it human activity, greenhouse gases, solar flares, who knows what? That's one issue. The other issue or question is the climate changing? Okay, now we have lots of data for this second one. You know, there's lots of ways to go back and reconstruct climates. Tree ring analysis, rat middens, stalactites, lake sediment, all those things have been used. And we have really, really, really good scientific evidence that our climate changes. Okay, this is the last 1,000 years. Okay, what's often shown by the climate change people is, or the human-caused climate change advocates is the last 100 years, that steep slope called the hockey stick. They're saying, oh my God, look at how the climate is changing. Well, if you bring this back to a larger scale, those are just different data sources up there on there, and go back and look at history and climate reconstructions. So here's the last 20,000 years, and this is a logarithmic scale on the bottom. So what that means is from the left to that first dashed line is 18,000 years, okay? And then 700 years, 200 years, so it's an increasingly broader scale. Now, what's really important here is you've all heard of ice ages, right? And the last ice age that hit us was ended about 12,000 years ago, and from 12,000 to 10,000 years ago, things got much warmer, okay? Last ice age out there. The interesting thing is that this is Northern Hemisphere temperature reconstruction, that the first 8,000 years after that ice age, you see that little bump on there called agriculture emerges, Mesopotamia flourishes. Compare that to where we are now. It was actually warmer and drier. So when you drive over to Gillette, Wyoming, fascinating drive, and you see all of that erosion that's out there, that was a desert back then. When it rained or the wind blew, all that soil, all that medium blew off. So that is, I mean, central Wyoming is just a massive erosion field. It's pretty cool. Of course, so is the Black Hills. That's what formed the gullies and everything here, too. Okay? That's what eroded all the soil away from around Devil's Tower. Okay? Then we went into a cool period, and then the medieval optimum. Okay? That was only 1,000 years ago. That's when the Vikings colonized Iceland and Greenland. And then we went into that period called the Mini Ice Age. Okay? That's when the Vikings in Iceland and Greenland died. That's when 75% of the known European population died due to starvation because of massive crop failures. Of course, they burned people at the stake because they didn't know about this stuff. They just thought someone put a hex on their crops. Okay? And actually, the Mini Ice Age ended officially in 1980. We are now moving into a warmer and drier phase. The question is, how big is it going to be and how long is it going to last? And that's where science gets really fuzzy because it's very complicated. Yes, there are greenhouse gases. Yes, there's changes in soil surface albedo. Plowed fields in the spring are different than green fields or cured grass field. They absorb more energy. The sun does funky stuff, okay? But the point is, when someone says the climate's changing, it should be, well, duh, it's always changing, okay? There is no such thing as a stable climate. As a matter of fact, if we go to the next step and reconstruct the climate back 500,000 years, which they've done with the Vostok ice core out of Antarctica, what you see is the Earth periodically has long ice ages and then these warm peaks. Okay, this is 500,000 years. The last 10,000 years is on the right side there. And interestingly enough, the last 10,000 years is the longest stable warm period in the last 500,000 years. Okay, and there's actually, been some anthropologists that have looked at this and says, we got fossil evidence of modern humans back at least 100,000 years. Why is it that we didn't get our act together until arguably the last 50 years or 100 years or 2,000 years, if we've been around that long? And the theory is we've only been able to develop civilization as we have when you're not worried about filling your belly, which means agriculture and a stable source of food and things like that. And it took about 8,000 years for us to domesticate cereal crops and animals and livestock and things like that to get to the point where we can think about things other than just feeding ourselves, okay? So, that puts a certain amount of severity into maintaining productive forests, agriculture, things like that, and the role that everybody here plays in managing their forest. Because for us to exist the way we are means a certain amount of stability. Stability in water supply, food supply, fiber supply, all of those types of things. So, I don't mean to turn this into a come to Jesus meeting, but there's a bigger picture. Now for Montana, we're most affected by what's called Pacific Decadal Oscillation. That's the temperature of the North Pacific, and we get these warm, dry periods. And from 1940 to 1980, we had an extremely long, cold, wet period. Lots of moisture. So what happened to our forests? They grew a lot. It wasn't just evil people putting out fires, okay? It was that we had the climate that was great for tree growth. And you take that into context of mini ice age and things like that. A lot of the forests, a lot of the old growth forests we see now are probably a relic of the mini ice age. Because prior to the mini ice age, they weren't here. It was too dry for them. So if we're going into a warm, and by the way, fires coincide with hot, dry periods, not cool, wet periods. And there's a similar graph, I may not have put it onto this presentation, done analysis for the Black Hills. And when you drive through the Black Hills and you see these waves of ponderosa pine this tall and that tall, regeneration of ponderosa pine very strongly correlates to wet summers. And your climate varies different than ours because we're affected by the Pacific, you're affected by the Gulf of Mexico. So your rainfall events are a lot different than ours. Pacific moisture doesn't make it this far, usually. So your climatic graph is a bit different. But fires, conifer regeneration, all correlate in the Black Hills very strongly with climatic fluctuations. Cool, wet, ample regeneration, no fires. Hot, dry, lots of fires, maybe mountain pine beetle. So, and this is just an illustration of these different warm and cool phases. They're analogous, they're tied in with El Nino and La Nina, which is equatorial water. But it just, and, to show you, just to demonstrate complexity, our sun is on an 11-year cycle too. And it goes through peaks and valleys. This is, 2013 is a peak. Okay, it's a weak one, but this is a maximum solar activity summer. So when you're trying to predict, okay, fire season, no fire season. Well, this rain's pretty good, but in Montana, we had a pretty low snowpack. We had a crown fire already in May, which is unheard of. So this rain has been a godsend for us, but our prediction is a lot of solar activity, more energy hitting the earth, hotter, drier summer. It's probably going to be a big fire year. So things to think about. When forests change. This is the Judith Mountains, central Montana, 1888. Look at those rocks on the right side as your reference. 100 years later. Okay? There's similar types of photographic records for Black Hills. Same types of things going on. And it is climate related. Now, does that mean we're a victim of climate? No, because our advantage as humans is by manipulating tree densities and tree distributions across the landscape, we can moderate climatic boom and bust things. We can provide trees with more water by thinning them. Now, naturally what would happen? They'd all get stressed, mountain pine beetle would hit them, and they'd burn. And you wouldn't have trees on that site, maybe for 400 years, okay? So that's the way natural cycles go. Our advantage, just like with agriculture and development and all those types of things, is we can help moderate some of these boom and bust cycles because, yeah, we don't do so well when things are in bust cycles. Examples of what's going on, this is not too far from here at Custer National Forest up in southwestern Montana. This is what it used to look like. This is several thousand acres. We had a fire called the Kraft Springs Fire that burned through there, killed a lot of trees, but we had a lot of fuel accumulation. And then it burned again. And that's what it looked like when it reburned, because same dry conditions, but we had all this additional fuel on the ground. Now we've lost ponderosa pine out of this ecosystem. What's our forest look like now? That's it. We have about 10% of what used to be there. And has not come back to forest. It's now brushland, grassland, rangeland. And cattle ranchers are going, yippee, I just doubled my cattle herd. Okay, so there are trade-offs. And it's all a question of what you want out there and really kind of what we tend to try to shoot for if you want stability is use a mixture of forest practices. So, and interestingly, a lot of our tribes are doing the best forest management because they're trying to manage to historic parameters where the tribal elders remembered, oh, there used to be an opening there. And so this is a management unit where some is left dense, some is thinned, some is opened. So now you're providing diversity of habitats, different age classes, and you've just created a very resilient forest ecosystem. You may lose some, but you won't lose all of it. It's just like investing. So really, you know, what you folks are involved with, the whole point of a management plan, going through these steps, doing things, is not to restore, which means to return to a former normal state. When people say, I want to restore my forest, my question is, restore to what? The mini ice age? Medieval optimum? 8,000 years before that when it was a desert? Okay, we have to be, conserving means to keep functional, to keep sustainable. And so we have to be looking at the future. And when you look out there and you see the mountain pine beetle, you see the fires, predictions are that will be our future. It'll be warmer and drier. So what do we need to do to our forests to keep them functional? And that first step is to look at what do we have, what are the risks, what are the things I want, and what can I do to moderate some of the events that are going to happen.